We discussed the notion about what a general tree is, and we would like to now talk about a special kind of a general tree, which is called binary tree. And I can tell you the fundamental difference right away. You can think about a binary tree is a tree, but a general tree is not necessarily a binary tree, because in the general tree, for every internal nodes, the number of child nodes can be arbitrary. Can be 0, can be 1, can be 2, can be 3, can be any arbitrary number. But in the case of binary tree, you can see the literal meaning. The number of child nodes for every internal nodes can only be up to 2. Can be 0, can be 1, can be 2. That's really the fundamental difference you want to keep in mind to begin with. Let's now go over some definition, and then we'll also talk about terminology and properties. A binary tree, or just BT, is an ordered tree. So ordered tree, remember the terminology we said before. If a tree is ordered, that means the order in which you arrange the child nodes, in this case 2 nodes, matters. And each node has at most 2 children. Can be 0, can be 1, can be 2. And in the case where you got 0 child nodes, that particular node is external node. And each child node is labeled as either the left child will be the first child, and also the right child, the second child. I'll visualize this very soon. And a left child precedes a right child, which means it comes before. That's exactly where the order comes from. And let's now try to define the notion of a binary tree recursively. Right? Either we got empty case or we got non-empty case. Let's visualize this right away. And I'm going to present in a very similar way as before when I try to show to you how you can construct from scratch a general tree in 3 different cases. And we also got the similar 3 cases for binary tree. I can also use this opportunity to really show you some simple terminology for binary tree. Right, so case number 1. Case number 1 is the tree is just empty. Empty binary tree, in which case, of course, the size is equal to 0. And how do we visualize it? You can either do just empty set, meaning that the collection of the nodes will just be empty, or you can say the root of the tree is simply pointing to null. Either way works, and this is just identical to how we did it for the general tree. That's case number 1. And let's talk about case number 2. For case number 2, let me use also green. That's also like a base case. For case number 2, it's more like a 1-node tree. 1-node binary tree. And in that case, the size would just be 1. Is equal to 1. And in that case, we'll simply say the root is actually pointing to some node over here. And the node is simply just the root of the tree over here. And of course, in a binary node, it would also be generic, but we do it programmatically. It can be storing any value over here, some value. That'll be case number 2. And it's very important to note, when you design an algorithm on a binary tree, typically it should be recursive, given that the structure for the binary tree is also recursive. Right? Let me write it down. So when you define algorithm on a binary tree, should be recursive, given that a binary tree structure is recursive. Let's now look at the recursive cases for the binary tree. Okay, recursive and also recursive. We'll talk about algorithm and also the binary tree structure. And when you define a recursion on a binary tree, either the tree is empty or if the tree contains only 1 node. In these 2 cases, typically that'll be the base cases, meaning that you can just return some result right away. And if the tree is actually larger than, for its size, larger than maybe 1 or 2, in that case, you may have to do a little bit more of a recursive call. Let's take a look of the recursive case. So that'll be case number 3. So case number 3, the size of the binary tree may be strictly larger than 1, meaning that it's more than the root that's really contained in the tree. So for case number 3, let me just box it right away. And the way I'm going to visualize it is like this. Think about, we have the root to begin with. And we have more than that, more than the root. And the root itself is going to contain either 0, 1, or 2 nodes. So that's a definition for binary tree. And we say that in general, the left and also the right over here, each one of them will just be another binary tree. So this is where the recursion comes from. So this will be just another binary tree over here, and this is just another binary tree. Okay, it's first of all really important to note. This will be the root of the so-called left subtree. Okay? Or we just simply has its acronym LST, left subtree. And on the right hand side, symmetrically, this will be the root of the right subtree. And the acronym for that will be RST over here. In the case where the single node actually contains 2 nodes, in that case, the left child will be the root for the left subtree, and the right child will be the root for the right subtree. Of course, sometimes you may it's possible you only have the left child or you only have the right child. But just in general, you may have to consider both subtrees over here. And when you want to run recursion, you can typically do some work with the root and then try to run the recursion on the left subtree as a strictly smaller problem, and then run the recursion on the right subtree, which will be another strictly smaller problem, and then somehow try to combine the recursion result from left subtree, right subtree, and also the root. That's a very general structure for designing algorithm on the binary tree. We'll see many examples later like that. Alrighty, let's now see a little bit more example about left subtree and right subtree, just give you a little bit more idea. And as I said before, the strategy for recursion on binary tree will be do something on the root and try to recur on the left subtree and also try to recur on the right subtree. Let's see just 2 simple examples. Let's say given this particular binary tree, if I want to calculate the size of the binary tree given the root over here. So what I can do is, for example, if I want to calculate the size of the subtree rooted at A over here is going to be, number 1, the A itself should be counted as 1. And then, number 2, it should be the size of A's left subtree over here, which means it's going to be the subtree rooted at B, which is the left child of A. You can think about, I'm just going to write a little bit more informally, A dot left child, LC, left child, plus the size of A dot right child over here. So this will be the right subtree of A. You can see the root for that particular subtree is the right child over here. This is the left subtree, and this is the right subtree. And in order to calculate the size of this entire tree over here, it will be, you can boil down into the 1, which is the A itself, and then plus the size of the left subtree and the size of and also the size of the right subtree. These 3 things together. Let's see another example over here, right? So we talk about how to calculate the size, and what if I want to search certain item that's actually in the tree, in the binary tree. Again, let's say I want to search, let's say certain item, let's say item in the tree rooted at A over here, right? How can I actually do that recursively? I can do something like, first of all, I check to see whether the item is already hitting A. If that's the case, I'm done. Otherwise, maybe the item exists in the left subtree, or maybe the item exists in the right subtree. Either way, it's either the item is already equal to A, or item exists over here, or item exists over here. So there are 3 possibilities. And one thing I want to clarify, you might be thinking, isn't there something called binary search we can do on a binary search tree? But remember, we are only talking about a binary tree. we haven't talked about the binary search tree just yet, which actually has to require a certain property called the search property. That will be the topic for next week, right? So here we're only talking about a binary tree only without satisfying the search property. I can write it down over here. This is just a binary tree without satisfying the search property, which we will talk about later, most likely next week. In that case, we will see that it's actually possible for us to really recur on only one side, but not both. Let me write it down over here. It's going to be something like a dot equals item possibility number 1, or we can search on the left. So a dot left child item, or I can just make some space for myself just to write one more line. Search and a dot right child the item. Right? So these are just two simple examples. You can feel free to turn them into Java code if you wish, but think these are very standard routines to really solve recursively. It would be very challenging if you want to solve this problem iteratively using a loop. Right, so up to now, we talked about the terminology of left subtree and also right subtree. And think about these two, the algorithm for solving these two problems over here. How you can actually try to break down the solution, break down the search space, or break down the problem space into the root itself, and also recursively on its left subtree, and also recursively on its right subtree. It will be very important for you to actually understand this strategy over here. Let me make a final annotation over here. So the B over here is the left child of A dot left child. And the C over here is the right child of A, the right child. And what you can see is for these two algorithm about counting the size and also searching the item, we are calling the recursion. Each one of them makes two recursive call. One will be on the left child, and the other one. So one will be on the left child of A, and the other one on the right child of A. And of course, for both recursive solutions over here, I have not included the base cases, which are important in order for the recursion to terminate eventually. Think about what's happening here. In both the calculation of the size and the search, if I start from the root over here, and of course I'm going to branch out to the left subtree and right subtree. Let's say in the case of branching out to the left subtree, itself will also recursively go onto its left subtree and also right subtree, right? And for its left subtree over here, it will also branch out to its left subtree and also right subtree, right? So that will be exactly how the recursion will work at the runtime. And in the case where the left subtree is already an external nodes only, in like a one node tree, that would be the base case. That's a very typical base case shape for the recursive algorithm on the binary tree, right? So there's basically a subtree with just one node. And how do we specify the base cases for our two recursive algorithm? Let's say for size, let's just say for example, let's say H is really an external node, right? External node. No further recursion is necessary. No further recursion necessary. Right? No further recursion necessary. And for the size of H, what should be its value? Since we don't need to recur any further, we can really specify just one value. It will be just one, just the node itself. On the other hand, if we want to calculate the search base case, let's say we are searching and the root of the subtree we are considering is rooted at H, and we are looking for item. Okay, I just noticed that I was a little bit inconsistent with the node and also the item, right? So why don't I just fix it very quickly? I can simply put the item over here as a second argument and then I can put A, the nodes, as the first arguments. That's what I can do. Okay, just to be consistent over here. And how can I check to see whether this external node is really equal to item? Well, just compare them. This will be, by definition, will just be, you can say h dot equals item. So these are the two base cases we have. This one here and this one here. So these are the two base cases. And for these two recursive algorithms, we have now completed their conceptual sketch about the recursive case versus the base cases. And you can really feel free to really turn that into Java code, which we are not going to do in the lecture because they're rather basic. If you got any trouble understanding or really try to implement this in Java, reach out to me.